Okay. Hey, everybody. So, welcome back. We're continuing to talk about chapter four. Um, and so, we're going to start off this video by talking about indifference curves. And actually, that's all we're going to cover in this video. And so, I'm basically going to start out before describing what an indifference curve is. I'm just going to basically show you how we make one. And then from there, we'll talk about what they are. So, we know from the last video, we talked about how a consumer can have the same exact utility between a number of different bundles, right? So, for example, the consumer can be indifferent between a bundle of 3 bananas and 2 apples, or 5 apples and 1 banana, or 4 apples and 2 bananas. Well, I'll pick a different point. Or between 3 apples and 2 bananas. Right, so we have 3 different points on the graph here. I apologize, my points don't look very circular, but hopefully the point gets across. So we have 3 different points, and they're all giving us the same amount of utility. Or in other words, we're indifferent between any of these 3 bundles of bananas and apples. And so what we can do is kind of connect these points by playing a little game of connect the dots. And this curve that we get by connecting these points is what we refer to as an indifference curve. And so it isn't just the 3 points on this line that all have the same utility. It's every other point that is on this line that has the same utility as all the other points on this line. Right? So we call it an indifference curve because the consumer is indifferent to any bundle that falls on this line. And so we can draw a number of different indifference curves all along this bananas, apples graph here. So these are all indifference curves. And now I'm going to talk about some of the properties or the characteristics of these indifference curves. And we're going to use the assumptions that we made about consumer preferences to be able to get at these characteristics. Okay, so the first one is that we can always draw them. And what I mean by this is that we're always going to find, so anywhere in this space where we have bananas and apples, we're going to be able to find points that are that our consumer is indifferent between, right? So the consumer may be indifferent between these points, and using our assumption of completeness and rankability, any point in this space that we choose, we can rank and compare to a different point, right? So we know that a bundle of 4 apples and 4 bananas is better than a bundle of 4 apples and 2 bananas because we can rank these, right? And we can also rank them in the sense that we know 4 apples and 2 bananas is as good as 2 apples and 3 bananas. And so we're indifferent between those 2 points, so they can fall on the same indifference curve, right? Whereas this other point that was better or has more utility will fall on a different indifference curve. So being able to rank every single bundle allows us to always be able to draw these indifference curves. We also know which indifference curves give us more utility. And the reason we know this is because more is always better. So since we know that having more of each of these goods is going to give us higher utility, we can decide that this indifference curve is at a lower point of utility than this indifference curve. And I'll show you by picking 2 points on these curves. So let's say we pick this point on this indifference curve. We have 2 bananas and 4 apples. Now, if we move up to this next indifference curve, we stay at the same level of number of apples, except for now we've increased our amount of bananas. And so since more bananas is always better, we know that this indifference curve that lies northeast is going to have higher utility. And so in general, we're going to be increasing our utility as we move to the northeast of this graph here. So our utility is increasing this way. We also know that indifference curves cannot slope upward, right? So I've been drawing them so far sloping downward, right? And we know they can't slope upward because more is always better. So for example, let me show you an indifference curve that is sloping upward and show why that wouldn't make any sense. So let's see, let's plot an indifference curve that slopes upward, and I'll just plot it like this, right? And this plot doesn't necessarily make any sense, and the reason is because we can pick 2 points on this indifference curve, one right here where we have, looks like about 6 apples, we'll call that 6, and 3 bananas. If we move along this same indifference curve, where theoretically we have the same utility, we can be at a point with 8 apples and 4 bananas. And since we know that having more of each good is always better, having more of both goods cannot possibly be on the same indifference curve, because we must have more utility if we're increasing both our bananas and our apples, right? So that's why we can't have an upward sloping indifference curve. Essentially, there has to be some trade-off for us. If we're getting more bananas, we have to be giving up some apples in order to stay on the same indifference curve, because otherwise we'd just be increasing our utility and therefore getting off of that indifference curve. Okay, and so indifference curves also cannot cross, and I'll show you this, and we know this because of the property of transitivity. Okay, so I'll draw out 2 indifference curves and make them cross, and then I'll show why it doesn't make sense. So this is what I mean by crossing. The indifference curves overlap. We can pick 2 points, or rather 3 points. One where the curves overlap, and 2 other points on each of the curves. We'll stick with those 3 points. And I'll label this one A, this one can be B, and this one can be C. So we know that because A lies northeast of B, that A has to be greater than B, right? So A is giving us more utility than B is giving us. Now we also know that C lies on the same indifference curve as A, which means that A is equal to C in terms of the utility we get from that bundle. And we also know, again, that B lies on the same indifference curve as C, so B is equal to C. But of course, we know that this can't be true because we know A is greater than B, and if A is equal to C and B is equal to C, and A is greater than B, something must be wrong, right? So something here just, it doesn't work logically, right? We could also look at a point over here, farther left on the indifference curve that is equivalent to A. Let's call this point D. So point D is on the same indifference curve as A, but point D lies below the indifference curve that's associated with point B. So in other words, D has lower utility than B, but has the same utility as A, and we know that A has more utility than B. So again, that can't work logically, and so these inconsistencies mean that we cannot have crossing indifference curves. And then finally, our indifference curves are going to be convex to the origin, and this is because of love of variety. So convex, again, is a convex curve looks like this, kind of shaped like a V. That's how we can remember it. And so I'll draw a utility curve that is clearly shaped that way. And so basically love of variety is saying that if we have a lot of apples, and actually I should maybe draw this a little bit better. So I'll draw a different one here. So let's do it this way. Okay, so if we have a lot of apples, let's say we're at this point here, we're willing to give up a lot of apples to go from 4 bananas to 5 bananas. right? So if we move from 4 bananas to 5 bananas, we're going right here and giving up, we'll call this point 10. I haven't counted them out. And this will be about 5. So we'd give up 5 apples to get 1 banana. But on the other hand, if we have only 5 apples to get 1 extra banana, we're only willing to give up, looks like, about 2 apples, from going to 5 apples to 3 apples. So in other words, we have a convex indifference curve shape because we want a good less the more of it we have, right? So if we have an abundance of apples, we're not interested in getting more apples, or we're more interested in getting the other good that we have not an abundance of, right? So in other words, the marginal utility of an apple is decreasing in the number of apples we have, and it can't be increasing in the number of apples we have. Now, the one exception here is that we could have a curve that is flat like that, perfectly straight. That's an acceptable indifference curve. What we cannot have is one that bows outward, because that would violate this kind of love of variety, in the sense that if we had this bowed outward curve, that would mean the more apples we have, the more we want to hold on to them. And so that kind of violates this assumption that we have. Okay, so let's shift a little bit. And we're still talking about indifference curves in a sense, but we'll talk about this concept of the marginal rate of substitution, or it's commonly abbreviated as MRS, and I may refer to it as that. And so the MRS, the marginal rate of substitution, is how much of one good a consumer is willing to give up for another good. And so let me remind you, slope, and just in the math sense, algebra 1, algebra 2, slope is telling us how much y changes when we increase x by 1 unit, right? So if we have a little graph here and we have a line, the slope is telling us if we move from an x value of 1 to 2 or 3 to 4, how much y is changing, right? If we have a downward slope, this is how much y is decreasing. If we had an upward slope, it's how much y is increasing. So our marginal rate of substitution is asking how much y are we willing to give up to get another x. That sounds a lot like the slope, and in fact, it is going to look like the slope, except for we're going to have a minus sign on top of the change in y, right? So change in y over change in x is slope. So essentially the marginal rate of substitution is the negative slope of the indifference curve, all right? And so we include the negative because we're giving up units of y to get to x, since we have downward sloping indifference curves. Yeah. And we'd like the marginal rate of substitution to be viewed as a positive number. So that's why we put the minus sign in front there. Okay, so there's this interesting interaction between the marginal rate of substitution and marginal utility, right? And so we talked about marginal utility in the last video, and we're going to come back to it here. So on an indifference curve, we know that our utility is constant, right? That's what the indifference curve is telling us. We're indifferent between all of those points. So moving from one point to another on the same curve, we're not going to change our utility. Our utility, the change in utility is 0 within one indifference curve. But we can write a movement along that curve in the following way. So the marginal utility of x times how much x is changing, right? So how much our utility is going to change based on a change in however much x we're giving up or getting, and adding to that the change in our utility from how much our y good is changing. And when we sum these up, they have to be equal to 0, again, because we're staying within the same indifference curve. So we have this nice expression that is equal to 0. So if we rearrange this and just subtract this second term here, we get that the marginal utility of x times the change in x is equal to the negative of the marginal utility of y times the change in y. And then we can further rearrange this to get the marginal utilities on one side and the change in y over change in x on the other side. And we see we end up with this negative slope again, which is exactly what our marginal rate of substitution between x and y is. And so we see that this marginal rate of substitution is equal to the ratio of marginal utility of x to marginal utility of y. And so kind of to think about this in an example, if our marginal rate of substitution is 2, that means that the marginal utility of x, MUX, is twice as large as the marginal utility of y. So in other words, the marginal utility of x could be 4. If the marginal utility of y is 2, that would reduce to 2, right? And so what the marginal rate of substitution is telling us is we're willing to give up 2 units of y to get 1 unit of x, which makes a lot of sense because the marginal utility of that 1 x unit is twice as valuable as the marginal utility of 1 unit of y, right? And so our utility would stay constant if we made that trade-off between units of x and units of y. Okay, so let's look at an example problem. We're given a utility function. So a utility function of m and s. We can think of these as M&Ms and Skittles again. And it's asking us to find the marginal rate of substitution between these goods. Right, so the first thing, marginal rate of substitution is equal to the ratio, MS is equal to the ratio of the marginal utilities. So M, marginal utility of S, over marginal utility of M. Now we need to find what the marginal utility of S is and the marginal utility of M is. So we have a utility function and we need to find the marginal utility of that. So to find a marginal utility, what we need to do is take a partial derivative. So I didn't make you guys do that math for nothing. So the marginal utility, or the derivative of this function with respect to M, is just going to be 2m, and since there's no m term over here, that part's going to be 0. We're just going to get 2m as the du dm, or in other words, the marginal utility of m. And then if we want to find du ds, the marginal utility with respect to s, or the marginal utility of s, we're going to just take the partial derivative of this function again with respect to s. So this is just going to be 4s, and that's our marginal utility of s. And so we just take the ratio of these two. And so the mrs of ms is equal to 4s. Oh, that's an 8. Let's see if I can erase that. I can. There we go. Get back to my pen. 4s divided by 2m. Or we can simplify this and make it 2s over m. So that's our marginal rate of substitution. And as you can see, it depends on the value of s and m. So we would, to find a specific marginal rate of substitution at a specific point, we would need specific values. And now the other part of this question is asking us, does m equals 4 and s equal 1, that's a bundle of m and s, fall on the same indifference curve as m equal 2, s equal 2? So what we can do is, if these 2 points or bundles are going to fall on the same indifference curve, they'll have the same utility, right? Because that's what an indifference curve is telling us. So what we can do is plug each of these points in, or these bundles in, to the utility function and see what utility we get for each bundle. If they have the same utility, then they're going to be on the same indifference curve. Okay, so let's find the utility of bundle 1. So this is m squared. Our m is 4, so that's 4 squared plus 2 times s, which is 1 squared. Okay, so 4 squared is going to be 16 plus 1 squared is still 1 times 2 is 2. So 16 plus 2 is going to be 18. So bundle 1 is giving us a utility of 18. Now we need to find our utility from bundle 2. So m equals 2, so this is going to be 2 squared. I'm just plugging this bundle now into the same utility function. Plus 2 times s squared. 2 times s is 2, so 2 squared. So 2 squared is 4. We have a lot of 2's here. 2 squared is 4, so 4 plus 2 times 2 squared. 2 squared is 4 times 2, which is 8. So 4 plus 8 is 12. So since these utility functions, since this utility function gives us different values for these two bundles, this means that these two bundles are not on the same indifference curve. No is the answer. And we can actually decide which of these bundles is preferable, right? So bundle 1 is giving us higher utility. So this person prefers to have 4 M&Ms and 1 Skittle over 2 M&Ms and 2 Skittles. Okay, so that's a little example there. So the next thing I want to talk about is kind of the shape of the indifference curve. And there are going to be 2 components to the shape, the steepness of it, and then the curvature of the indifference curve. And both of those aspects are going to tell us things about the indifference curve. Okay, so the steepness is going to tell us about the relative value of the goods to the consumer. So this is telling us about how the consumer values each good. So let's start with a flat curve, and then we'll do a steep curve. So a flat curve is going to look like this. So these curves are relatively flat. Although you can still see there is some curvature to them, but they lay flat. And so what a flat indifference curve is telling us is that we're willing to give up a lot of x to get one more y. So let's think about getting one more unit of y. So let's say these are the units of y. We want to move from, let's say 3 to 4. Well, to do that, if we're on this bottom indifference curve, if we were originally at 3, we have this much x. So let's just call this x1. And now if we want to move up to having one more unit of y, or 4 units of y, we will have to give up a lot of x to get to now x2. So we'd be losing all of this x to get one more unit of y. So in other words, this is telling us that this consumer values y more than he values x. The other way to look at this problem is to say, well, how much is he willing to give up? How much y is he willing to give up to get an extra unit of x? And so we can answer this question as well. Let's pretend, and this is going to get a little messy, so hopefully I can do this well. Let's pretend like we want to move from this point, x3 to x4, right? So we want to get one additional unit of x. How much y are we willing to give up to get that extra unit of x? So I'm going to go up to a different indifference curve up here so that it doesn't look as messy, right? So if we look at this, the change in our y to get one more additional unit of x is very small, right? So we're not willing to give up much of our y to get one more additional unit of x. So looking at it that way is still telling us that this consumer is valuing y more than he values x, because he's willing to give up y, much less y to get one unit of x. Okay, and so the flip side of this is we could have a steep curve, and this is going to kind of look the same way. So we're going to have a steep curve here rather than a flat curve. And another way to think about steep versus flat is we could just flip the axis, right? So if I wanted to, I could call this good X and this good Y, and we'd have kind of a steep flat curve reversal. But if that didn't make sense to you, that's fine. So a steep curve is telling us, again, something about how much we value each good in relation to the other one. So last time when we had a flat curve, we valued Y more. In this case, to spoil it, we're going to be valuing the X good more than the Y good if we have indifference curves shaped like this. So let's again look at an example of how much X we're willing to give up for one more unit of Y. So again, let's say we are moving from 3 units of Y to 4 units of Y. How much X are we willing to give up in order to do this? So if we are originally at 3 units of Y, we're at this amount of X, X1, and we want to move up to Y equals 4. So we want to move up and get one more additional unit of Y. How much X do we have to give up to do that? X2. So we're losing this amount of X in order to get one more unit of Y. So we're giving up quite a bit more X to get this extra unit of Y. Whereas if we look at, let's see, going from, let's say 6 units of X to 7 units of X. So how much Y do we have to give up in order to get one more unit of X? Let's look at this third indifference curve here and see. So here's where we would be on the Y-axis if we have 6 units of X. Let's call this Y1. So this is where we'd start in terms of how much Y we had. So we have a bundle of 6X and Y1Y. In order to go from 6X to 7X, we have to move down to this point here, which I apologize is going to look a little messy. And we'll call that Y2. And so we're giving up this vertical height. That's the amount of Y we're giving up in order to get one more X. So in other words, we're willing to give up a lot of our Y to get only one more X. So again, that's telling us that we are valuing the X good more than we're valuing the Y good. Yeah. And so one way you can keep, you don't have to memorize what the steepness is telling you about valuing X versus valuing Y. You can just graph these things out and do the little example that I showed to just remind yourself. If I think that's the best way to do it, because this is fairly intuitive in terms of looking at basically the slope of the indifference curves. Okay, so like I said, curvature is also important. That's going to tell us something about the indifference curve. And so the indifference curves can be relatively straight or relatively curved. So we'll start with relatively straight indifference curves. So let me draw a couple of these. So I'm going to draw them with a little bit of a curve, but mostly just straight. So there are a couple indifference curves. Okay, so one thing you can notice is that the marginal rate of substitution does not change a lot throughout the curve, right? So what I mean by this is that the slope, so one more additional unit of X, we have to give up about the same amount of Y for each additional unit of X. Now it does change a little bit, but not by a lot throughout the curve. That'll change when we look at a more curved indifference curve. So in other words, to reiterate, we're willing to give up about the same amount of Y to get one more X, regardless of how much y we have, right? So regardless of what point on the indifference curve we're at, we're willing to give up about the same amount of y for the same amount of x. And so what we label these goods as is substitutes, right? So substitutes are similar goods that fulfill a similar requirement. And so we should be willing to give up a certain amount of substitute for the other and basically not care about which one we have. We just care about the quantity of the sum of the two goods, right? So in other words, if you think of, let's say, a lime and a lemon as about the same good, they kind of fulfill a similar role. You can use them for similar things. They're both citrus fruits, right? If we think of these as very close substitutes, it doesn't necessarily matter which one we have as long as we have one. So we're always going to be willing to trade off some ratio of limes to lemons and be just as happy or remain on the same indifference curve. Now, the extreme version of this is if we have perfectly straight lines. So if our indifference curves had no curvature to them at all, they were just straight, flat line. If we have perfectly straight lines, that's indicating that the two goods we're looking at are perfect substitutes rather than just close substitutes. And so perfect substitutes are kind of silly to think about, but one example would be a 2-pack of batteries and versus a 1-pack of batteries, right? So you'd always be willing to trade off in a 2-to-1 ratio, a 2-pack of batteries for 2 1-packs of batteries, right? Because you'd be getting 2 batteries regardless of what you do. And so those would be perfect substitutes. Okay, so like I said, we could also have a very curved indifference curve. So let's look at this. So obviously this is much more curved than the previous indifference curves I drew. And I'll just draw one more for completeness. And so this is telling us that what we're willing to give up for one more unit of x, so how much y we're willing to give up for an additional unit of x, depends heavily on where we are in the indifference curve. So in other words, if we have very little x and a lot of y, we're willing to give up a lot of our y to get one more unit of x. Whereas if we have a lot of x and relatively little amounts of y, we're willing to give up very little of our y to get an extra unit of x. And so basically this is telling us that how much we value x relative to y depends on how much x we have and how much y we have, right? And so that's what we call complements, right? So we can think about peanut butter and jelly, P, B, and J, right? So PB is one of the goods, J is the other, peanut butter and jelly. So let's just call this one PB and J. If all you have is a bunch of peanut butter and you don't have any jelly, you can't make peanut butter and jelly sandwiches, right? Whereas if all you, and then of course, if you only have jelly and no peanut butter, you can't really make peanut butter and jelly sandwiches. Of course, peanut butter on its own can be used for other things, as can jelly, but our utility is greater if we can use them together because they are complements. And so that's a good example of a complement in the sense that if we have a ton of jelly, we're willing to give up some of that jelly to get a little bit of peanut butter so that we can make some peanut butter and jelly sandwiches. And same thing is true with if we have a lot of peanut butter, we're willing to give up quite a lot of our peanut butter to get just a little bit of jelly so that we can make a peanut butter and jelly sandwich. Now, if we have perfectly curved lines, now it's kind of going to ruin the curve a little bit because it'll look like a right angle. That's what I mean by perfectly curved line. That's going to tell us we have perfect complements. And so the kind of typical example of perfect complements is right shoes and left shoes. And essentially, only having a left shoe is essentially useless and only having a right shoe is essentially useless, right? You need both of the shoes in order to have a functional pair of shoes, essentially, right? So what this kind of perfectly curved indifference curve is telling us is that our utility is constant every point on the curve, right? So if we increase the amount of right shoes we have without changing the number of left shoes we have, that doesn't increase our utility at all, right? The only way to increase our utility is to add one right shoe and a left shoe, right? So if we add a left shoe, that doesn't give us any more utility. If we only add a right shoe, that doesn't give us any more utility. If we add one of each, then that does give us more utility. And so that's perfect complements. And I believe this is where we're ending the video here. So I'm going to stop share. There will be 2 more videos or 2 more sets of videos covering chapter 4. We'll get to those some other day. So that's all for today. Thank you.